Hi everybody, and welcome to the second half of the semester. And today it's going to be a really cool tutorial because we're going to shift a little bit and not talking about electricity and talking about magnetism. And the really fun part is right now the semester is becoming really easy because all the concepts that you already learned about electricity are going to be valid also to magnetism. And it's also always going to remind you something before and what we're going to do now, and you can compare and understand better what is actually electromagnetism, which is one topic. Before we're going to start, I want to show you some really cool video about our topic today, Lorentz Force.
Standard radiation therapy is an effective way to treat many cancers, but it isn't perfect. It kills cancer cells, but it also kills some healthy cells in its path through the body. That's just one of the reasons Mayo Clinic is bringing a new type of radiation therapy to its patients. It's called proton beam therapy, and it has the potential to cure more cancers with greater safety and help people live longer. Doctors have used radiation therapy to kill cancer cells for many years. The standard technology fires X-rays or photons at tumors in hopes of eradicating them.
The downside to the X-rays is that they pass all the way through the body.
Mayo Clinic Dr. Robert Foote says that means the radiation also kills healthy cells. This limits how much radiation you can safely give to patients because it could damage surrounding tissues and organs. But a new technology called proton beam therapy is more precise and therefore more effective. Dr. Foote and Dr. Stephen Schild head the Mayo Clinic Proton Beam Therapy program.
A proton is one of the key constituents of matter.
They're like little bullets that can be made to stop when they hit tumors.
The way it stops in tumors is you have to aim it properly and you have to give it the proper amount of energy so it stops in just the right place.
This massive machine is called a synchrotron. It accelerates the protons to near the speed of light and fires them into the body.
Okay guys, so welcome to our tutorial today. So what we're actually going to do in the first question is actually understanding what is this device and how it's related to our topic today, Lorentz Force, and how we can save life by understanding magnetism. So the problem with using the standard X-ray radiation therapy is that radiation of X-ray going all the way and eradicate whatever comes in the way. For example, if this is your skin, right? This is your skin, and here is the cancer. So the X-ray will come all the way to fight with the energy, yeah? Let's talk about energy terms or power. Come all the way to kill this, whatever comes in the way, all the tissue that you have in your body until you get to the cancer cell. But when you use proton beam therapy, actually, it can skip on the skin and just have a lot of energy when it's come to the tissue. So if we can learn how to accelerate this proton and move them in a specific velocity that we need, we can actually do that and save a really sensitive places such as brain cancer that you really don't want to mess up with the rest, the things that around the cancer cells. Okay, so let's draw this thing, okay, from a top view. Okay, so I'm moving to this board. So this device called the cyclo. What is cyclo? It's circle, and cyclotron. Tron is mean device, instrument, tron. And the devices look like a huge D. See, this is D, and this is another D, okay? The right D, the left D, okay? And these D are actually huge magnets, okay? And I want to show you the direction of the magnetic field that they produce. They produce magnetic field that actually come inside the board, okay? So I'm going to draw a vector that's going inside the board. And I want you to think about the magnetic field as you used to when it comes to electric field and wind and stuff like this. So think about that wind of magnetic field going inside this plane. Good. And here, between the space, there's a space between these two plates, and I apply here voltage. And I know this sign of a battery is a little bit weird. We're going to explain what this sign of a battery actually means. Okay? And here the distance between these to this is small d from the word distance. Great, great, great. Okay, so I'm gonna take a proton and put it here. Okay, this is a proton. I put it here. There's a change of voltage of the battery. Here's the change of voltage between this point and this point. Okay, this is voltage V node. This is 0 voltage. Okay, and the first question I want to ask you is, what is the velocity that this proton gonna have when you reach this place? Okay, this is the first question. I'm gonna go to this board. Okay, so what is the final velocity of the proton? Okay, so what do I mean by saying that? When you look at the proton actually is here, and you have a positive charge, right? Proton are positive particles, and when he stands here, he actually stands on the top of a mountain. You have a voltage, right? So this voltage actually accelerates this proton to this area, right? It's like somebody that's standing on an airplane and jump. That's what's going on, right? If you're going to be free in the sky, you're actually going to jump, right? So how can I find what is the velocity here? Do you have any idea? If it was physics 1 and I want to understand what is the velocity of this pen falling, how I would find the velocity? I'm going to use conservation of energy. So I'm going to say that the energy that I have in this place must be equal to the energy that I have in this place. In this place, I'm going to have only potential energy, right? Like mgh, right? But in electricity, we don't write mgh. We're going to write Q multiplied by V, right? This is the energy term. And on the other side of the equation, what I'm going to have? I'm going to have only kinetic energy. Perfect. And this is the mass of a proton, right? And this is the velocity, square. Great. So from this term, I can actually really easily can calculate what is the velocity. The velocity happens to be square 2q the battery power divided by m, right? And you're going to understand it later, but let's call it V sub 1, okay? Cool? That means that there's going to be a lot of velocities. So this is the velocity this particle going to experience, okay? Going back to this board, okay? So here, it's going to have this kind of velocity. Perfect. So now the particle going to enter this zone, you see? And now it's going to experience another force, okay? This is going to be not the electric force that accelerates it, the magnetic force. And the magnetic force, I want you to be really careful, okay? Some of the topic in magnetism really easy compared to electricity, and some of the topic of electricity more easy than the one in magnetism. So this is the case of the force. The magnetic force, which called Lorentz Force, is really similar to the force we experience when we have electric force, which is Q multiplied by the electric field, right? So they're going to be really the same. So the Lorentz force is, of course, a vector. Have Q. If you don't have electrical charge, you don't going to have any force. I also need to have the magnetic field. Magnetic field is sign up with B, okay? So until now they are in the same level, right? Now comes the catch. The catch is that I don't need you to have charge and the field, charge and the field. I also want you to have a velocity. If you don't have a velocity, we cannot talk, okay? Charge with 0 velocity, this force is going to be 0. And now comes the second catch. The second catch is we have here a vector and here a vector. Okay, so I actually gonna be care about this vector. What is the cross product between these two? Which means I really care about the angle. If the angle of the velocity and the magnetic field is 90 degrees, perfect. Sinus gonna be the strongest. But if they are in the same direction, it's gonna be 0. None, okay? So this is the two things I want you to remember, and a really easy way to understand what's going on here, where's the direction of the force. You know, we have this cross product. We need to understand what's the vector that's going to be given to us. So we have, yes?
What is B?
B is the magnetic field, is this, okay? Great. B is the magnetic field, is the electric field, okay? Yeah, I understand it should be M, right? But this is B, okay, from historical reasons. Good. So I want you to understand what is the direction of the force, because here it was really easy. It's just the direction of the electric field multiplied by plus or minus of the charge. But here we have some fishy thing, right? So the trick to understand it is using the second hand rule, okay, this one. So how the rules go, I'm going to show you my tricks. If somebody is doing a good job, I'm going to do this, right? V. Okay, really good job, V. So you're going to put your thumb in the direction of the velocity. In our case, this direction, velocity, right? It's going that way. Perfect. Then I want you to imagine that you have a gun which shoots magnetic fields, okay? So this is this finger, okay? So the magnetic field is going to follow the X. The thumb needs to follow the velocity, right? And last but not least, the force is actually to give somebody a slap. It's a lot of force, right? Boom, slap. Slap is in this direction, right? So the slap comes outside of the center of your hand. So again, velocity, magnetic field, right? Pew pew, a gun, and the force in this direction. So if I'm going to take my hand and oriented myself in that manner, so velocity, magnetic field, and force, I know that the force is going to do that. It's going to give a slap to the particle and that direction. Cool? Understood? Just a summary. Force, velocity, magnetic field. Okay? Second hand rule. Perfect. So if it's going to happen, it's going to get a punch and going to be in that direction, right? And now it's going to have a velocity in that direction, right? So my question to you is, what's going to be actually the path that the particle is doing? So the next question is, what is the path that the proton will do, right? And now let's see what's going on, okay? What's going on this? Put V here, magnetic field here, boom, a push at that direction. The particle gonna end up here, and again, and again. So what this kind of shape, this is actually a circle, right? It's a circle. It didn't succeed to finish the circle, and what's going on? You're gonna get out, right? So I want to know what is the shape, and we talked about that the shape is actually circular shape, right? And if I want to explain what is actually the shape of a circular motion, what is the parameter that I need? The only one for a circle is the radius. So let's find the radius. Okay, so what is the path of the proton? So I'm gonna go to that board. So it will have circular motion with radius of, let's find it. So circular motion, do you remember the equation? Newton's law for circular motion is mass times acceleration, which is always whole. And when we talk about acceleration inside a circle, so it's actually mv squared divided by r, the radius, right? And this is equal to what? To the force. Which force we have in this part? Only Lorenz, which is QV multiplied by B. Note that I already did the sign. The sign of 90 degrees is 1. So only magnitude, V and V cancelled out. And I can write that the radius, R, is equal to mv divided by qb. Question? There was a question? Okay, perfect. So this is the radius. What do we see here? that the radius depends on the velocity, which means if the proton would come with a lot of velocity, the radius is going to be huge and large, but if you're going to come with the small velocity, it's going to be short and small. Okay, you got it? So this is the point here. Perfect. So how much time it's going to take to complete this cycle? Half of a cycle. Let's do it. Our next question. I'm going to go to this part. So what is the time? What is the time? Is the time to finish this semi-cycle, right? What is this time? Delta T. How we can find it? It's actually, we know that it's not the full time of doing a circle, right? It's not capital T. It's T over 2, first of all, right? It's half of the cycle. And how we can find T, time? We know that T is actually distance divided by velocity, right? So what is the distance of a whole cycle? 2 pi r, right? 2 pi r. Not the area, the,
It's half.
yes, it's half, but I already wrote the half. Good point. And what is the velocity? V, right? We just calculated. And if I'm going to plug in whatever I know, this half, 2 pi, and we know R. What is R? We just found that it's mqb multiplied by V divided by V. And then I get something really, really cool. 2 die with 2. But V die with V. So the time that's going to take to complete the cycle is pi, which is constant. M of the proton, which is not going to change. It's a proton. Okay? Divided by Q, which is the charge of the proton, not going to change. Divided by B, which is the magnetic field, which I choose. I bought the magnets. Right? So this time is the same. Which means no matter with which velocity the proton going to enter this D shape, it's going to get out at the same time. This concept is clear? This is genius. That's what makes this device super genius. Because what's going to happen? So the particle going to enter the D, do half of cycle, okay? It gains some velocity here, right? And then you know what it's going to do to the battery? Hop! I'm just going to take this plus minus and hop, switch it. Now this is plus, this is minus. And the proton stand here and said, oh fuck, I'm on top of the world, at the top of the mountain. I'm right now free fall. And it's going to accelerate. But it's not going to accelerate with the same velocity. It starts with this velocity that it had before. And then it's going to spend time here, which is going to be the same time, right? And then it's going to get out. And what's it going to do with the battery? Going to switch it again. And then the proton going to accelerate how much that I want. Is that concept is clear? So that's the way we can accelerate particle. And that's what people do in the big acceleration that we have in Germany and France and collide particles to learn the physics. That's what they do. Okay? Cool? Good. So we found this thing. And now I want you to find what is the second radius, right? It's coming out, you know, not the second radius, but what is the velocity that is entering here? Okay, what is this velocity? Let's go to that board. Okay, so what is the final velocity of the proton in the second T, at the second round? Can, right? So we're going to say U initial equal to U final, as before. You have potential, but what it's also got, you got the previous kinetic energy that it accumulated in the first time, right? And what we're going to end up with? New velocity, right? Which is going to be bigger, right? Because what we're going to get is this. We're going to get this solution, V2 equals to, first of all, going to be a square, because we're going to take off this thing, right? And we're going to have this to be v1 distance square plus 2qv divided by m. So actually the velocity increased, right? What's going to happen to the radius? Let's go to this board, okay? So what's going to be the second radius? What is R2? R2. So it's going to be the same. Here we're going to need to put R2, V2, V2. So this is R2 equal to V2. So the radius is going to be bigger because we have more velocity. Is clear, this concept? Let's go to that board. And what is the time it's going to spend there? I'm going to show here. So it's going to enter here with much bigger velocity, right? And it's going to have a bigger radius. This is R2. It's not a good color for that. Let's use the green. So you're going to do a bigger cycle than it did before. This is R2. And this is the small R1. You see it? And here it's going to get out again and going to repeat the cycle again. Okay? Is that clear? What is the time it's going to spend here of the second one? The time it's going to take him to do this journey? It's a longer journey. The same time, because the velocity is going to compensate for that. Right? Is that clear? Genius, right? A genius device. Good. Perfect. So now I want to do another something that's going to relate to circular motion. I'm going to ask you, what is the angular velocity? It's going to be really important, angular velocity, and I want to do some recap of what we learned in Physics 1, so it's not going to be a challenge, okay? So I'm going to clean this thing. So what is the angular velocity of the proton? What is angular velocity? Remember the definition? Angular velocity is how much angle I succeed to do in a specific time. It's really similar to velocity, angular velocity, right? Instead of talking in meters, we're talking in radians, okay? If I'm standing in the middle of the cycle, I look for somebody, for the proton running. So the question, angular velocity, is how fast do I move my head to follow the proton? If it's going really fast, this is my angular velocity, right? If it's really slow, it's that, okay? So what is equal to? So we can calculate it really easily. We can put here difference in angle, for example, complete cycle and starting a cycle, theta final versus theta initial, and the time, final time versus this, right? This equal to what? So this end up to be 2 pi, and we just found that one. It was here, right? This was half time, so I'm just going to multiply by pi m qb, right? This is t, these two together, this dying out, and what do I have? I have that it's constant. The speed rate that I'm moving my head if I'm in the center of the circle, following the proton moving, right? So it's a constant, qb over m, okay? Is that concept is clear? So this is the angular velocity, which is constant. Okay, another question. What is the final velocity that the proton is going to have? The final one. How we can find it?
Conservation of energy?
Yeah, but it's going to be a really pain in the ass. Think about that. We need to do it again and again and again each time for the next radius, right? Taking the initial velocity from previous time and do it like a for loop in a computer. We can do that. But I got another way to do it. So, what?
Do we know the final?
Yes, we do know because we designed the device. Okay, so somebody here already implicit something. He said that if you know the radius of the device, the final one, so you can use this idea. And to the ones that didn't understand it yet, let me explain it to you. So what he said that thing. Remember omega r? If you're going to multiply it by r, right, because here I have radians. If I'm going to multiply it by meters, right now I expect here to have a velocity, right, in terms of units, right? This is radians versus time, and this is right now meters, right? R multiplied by omega. What is actually omega? We just said it's d theta divided by dl. But what is r divided by, by dt? But what is r divided by dt is actually the velocity, right? So this is the velocity. Sorry for that. Misconception, okay? So this is d theta, this is r. What is r d theta? This is, just remind you, this is r, this is d theta. So what is r d multiplied by d theta? Is this, dl, right? Small movement on the, the perimeter, right? So this is dl. What is dl divided by dt? Is the velocity it's taking me doing that. So this equal to velocity. So the formula here is actually v equals r omega. So no matter which radius I am, I can immediately extract what is the velocity. And especially if I know that the final radius of the device is capital R, so v final, which means v at radius r, is just r multiplied by omega, which equal to, we know r, it's a given, and we know omega, it's q b divided by m. Okay, so this is the final velocity. Let's calculate it. I'm going to give you some numbers. Okay, the radius of the device is 18 meters. 18 meters, it's a huge device. Think about it, that I'm the patient, I'm sitting in the bed, look at the picture. Sitting in the bed, and in the other room, there's 18 meters, okay, of radius. It's a huge. The charge of a proton is like the charge of the electron, right? But with the plus sign. It's 1.6 times 10 to the minus 19. Really, really small, but don't forget we're going to divide it by something even smaller. The weight of a proton, which is 1.7 times to the 10 minus 27. And the magnetic field, it's going to be 0.46. And don't confuse, it's huge magnetic field. 0.4 Tesla. Tesla is a gigantic unit. It was a gigantic person, okay? But you have also a gigantic unit. So if you see 0 point something Tesla, you say, fuck, this is crazy. When I work on a device, a medical device, I learned that you cannot use 6 Tesla near to humans. It's dangerous. It's such a strong magnetic field, okay? So this is a huge magnetic field, okay? Perfect. So let's calculate it all. What we get? Somebody can help us? So the final velocity is? Somebody do it? Okay.
79 million?
Again?
779.
But we are engineers, so let me put 79 into 8 times 10 to the 8. What's fucked up with this? What's fucked up with this size?
That's faster than light.
It's faster than light. Okay, what I want to say, that this device is actually so good, so strong, that he accelerates this proton to the velocity of 7% of the speed of light. Okay? So all the calculation that we did was really good until some point that it was not good, because we get close to the speed of light. Okay? Really close to the speed of light. So remember that, I don't remember if you, in physics 1, you learned about Lorentz transformation, which deal with velocity exceeding, getting close to velocity. Lorentz, it's the same person, Lorentz, okay? So this device is so good that the calculation that we did in the bigger radiuses not holding anymore. Okay? Great. So far, this was the first question. We did a calculation for a charge, and I want to show you some cool demonstration. So this is, if you can plug out the electricity from the camera, because this is going to be a really high voltage demonstration and really dangerous. So what I'm going to do is I'm going to show you electron beam, okay? You don't see, it's the other way. Okay, so you don't actually see electrons. You cannot see, but you can see them interact with the light. So you see this cool beam, and if I'm going to bring magnets nearby, I'm going to deflect by Lorentz force and do a curve, right? So let me see if you see it. You see that I do some angular velocity? You see it? Does it change? Good. So let's close it. Great. Okay. So right now, this was the first demonstration. You can plug in the electricity. Good. And right now, I want to do not the point charge Lorentz force. The second question is regards what's happened to a beam when we have a beam. Okay. So let's do that. So in this question, it's a shorter question. We have a door. Okay. Let's do that. Let's clean this. We don't need this anymore. Okay, we have a door, and the door has size of L on L, right? L on L, and in our space there's some magnetic fields. The magnetic fields have the formula of function of x, which is some constant divided by x. Okay, got it? Some constant divided by x. In which direction? Because it's a vector, in the y direction. Let me draw everything for us. So this is going to be the z coordinate. This is going to be the y coordinate, which magnetic fields actually fly the direction. Magnetic fields going in this direction, but it's getting weak and weak as you go with the x direction. If you go at the x direction, the magnetic field getting weaker. You see it? Stronger here, weak here. Got it? Perfect. And let's draw our door. So this is the door. Okay? Let's do a 3D. Okay, this is our door. Okay, great. So the door have each side L. The door starts in location which is given A, and any location which is B, and the distance here is of course L. This is our door. Okay. And the first thing I want to ask you is, what is the force apply on just a beam? Okay, regular beam. So let's do that. So first question, what is the force on beam with current? So we have what, let's do it in this place. What is the force on a beam with current? And you already learned what is current. What is current? We do it by I, and it's the change in charge versus time, right? Charge is passing by in some time, right? Good. So we have some beam. This is the beam. Really ugly beam. General beam. And we have a current I inside it. And we want to understand what is the force applied on the beam. So the way to do it is not asking what is the force applied on all the beam. Let's deal with a small part of the beam. This small part have not the total charge that moving in the beam. We have a small amount of charge, right? dq, right? And we have in space magnetic field in some direction, right? Because we in the class of Lorentz, so we're actually interested in the force which magnetic field extract on beams or particles. So what is the force that this charge would feel? What is the force? So of course it's a small force because we're talking about this small charge. Remember the equation? The equation of Lorentz was Q multiplied by V, exactly. We need the velocity multiplied by B, but B is a vector, so we need to say which kind of vector multiplication we want. If this is a vector and these two vectors, we must have the cross multiplication, right? So it's df multiplied by dq multiplied by the velocity of this charge, right? Multiply in a cross product by the vector, right? Perfect. And what is the velocity? What's the definition of velocity? Distance versus time. So this term is actually dl divided by dt, right? Multiplied by dq cross b. Is this friend is familiar to you?
Current.
It's a current in all the wire, right? All the beam, all the wire, right? So we actually get that each force that this beam actually feels due to the charge and the magnetic field and the velocity that the charge actually moving. They are moving in some velocity because this is a current, right? So this force is actually equal to I dl cross B, right? And if you want to find the force, the total force that this beam actually feels, so it's just the integral. This is sum of its part, right? So let's do it here because this is a big equation for us. So F equal to the integral of dl cross B, and note that on each part of the wire the current is the same, so I take it outside of the integral. Really important equation, okay? So let me show you that this thing is real and I'm not joking with you around. So here we have demonstration. Yes, we got it? So you don't need to plug the electricity, it's okay. This is a safe one. I'm gonna just use 9-volt battery. This is insane. Here we have a wire. You see the wire? This is a wire. And these red and blue things, right, are actually, here too, are actually magnetic poles. Okay, positive, north and south, okay? And I'm gonna take the battery. Cameraman, you see it clearly? Let's stop it from moving. I'm gonna plug it to the electricity. So, let me see if you see something. Oh, fuck, okay? This is not ghost, this is actually a force. Okay, I can apply force on the beam. All the charges, right now there's charge in the beam. Right now there are charge in the beam, but they're not moving. They're just having fun, okay? They're actually moving, but in random motion, yeah? But when I apply the voltage, they have electric field. All the guys said, dude, I feel like falling that way. And they start moving, okay? And then what's going on? When they're moving, we have current, which result in force, okay? What's going to happen if I'm going to change the battery, right? Put it that way, but I'm going to flip it. What's going to happen to the force? It goes the other direction. Let's see if it's working. Ah, it's crazy, right? It's insane. Okay, for me it's like insane. And this manner is how motors in cars work. The same concept. You have a magnetic field that's changing all the time to keep it moving. That's the concept of a motor. Mechanical engineers, right? So it's really important, okay? Good, so we found the force, and I want to talk about the really standard case, which is gonna show up in exams and homework a lot, is what is the obvious angle to have, and the shape of the wire. This is the shape of the wire, you see it, dl. It's for every wire, yes? But if it's gonna be a really straight wire, this integral would end up to be L, right? If the magnetic field is constant, it can get outside of the integral to be B, and this is I. So if you have just straight line of a beam, not a really crazy wire, just a beam in a magnetic field, this is the force that's gonna apply. In what direction? What rule we have? The right hand rule, the second right hand rule. Next week we're going to learn the first one, right? And the only thing that change is that I is actually presenting the velocity, okay? It's the same concept. This is right now I, okay? So that direction, magnetic field, and that direction, the force is, boom. this would go in that direction. All the wire. Good? The same thing happened here. We know the direction of the current. We can calculate what direction the beam would want to go. Okay? Good. So I want to find what is the force that's going to happen to this door if I'm going to put here a battery. So if I'm going to put here a battery, let's draw this in a more explicit way. So if there's going to be a battery here, with the plus here, there's going to be electric current that go in this manner. What's going to happen to the door? The door would experience a force, and it's going to move, going to open. Okay? So that's what I want to do. I'm going to this part of the board. Okay? So what is the force that apply on the door? So let's make our life easy. Okay? Steve Vai taught me that every big solo on a guitar that you see, just take the parts and take the big problem and divide it to parts. Okay? To simple one. So this is going to be called right side of the door, left side of the door, up and down. Are we clear? This is good? So let's solve it. So what is the force on the right part of the door? What is it? Is current, right? This equation, integral dl, which is vector. I didn't say it, but this is vectors. You have a cross product between them. They are vectors. dl cross b. Good. Okay, so the only thing you need to do to solve the equation is to understand who is dl and who is b. Okay? What is b? It's given. b naught divided by what? By x. But on this beam, x is constant, right? We're talking only about the right beam, x equal a. And what is the direction? The direction is always the y direction. Okay, it's given. Good. What is dl? dl is the right one, right? Of course, this is the right one. This is. So we're talking about dz. So this is actually dz. In what direction? In the positive direction. Right? That's it. That's all the thing we need to solve. Right? So this is a constant. Can go outside of the integral. Right? Divided by a. Divided by a, right? What is the cross product of these two? X, Y, Z, right? Remember this cycle of the clock of the cross product, right? So if I'm going to do ZY going to give me X, but because I work on the other side, it's going to be minus X, right? And this is integral of a constant, right? What is the boundaries that we have? It started at 0 and end up in L, so actually we have here L, right? And don't forget this I. So this is the force that the right beam experiences, right? Agree? Perfect. Let's move on to the next one. So what the left experience, I'm going to this direction. So right now, this one, so we have the equation, the same one, F L equal I integral from 0 to L, the lowest value, the highest value, dl cross B. So B is right now changed to B not divided by small b, which is the place where this beam is located. And what is dl? dl is again dz, but right now the current is going in the down direction, right? Minus. Up and down. Right? Good. So the same thing going to happen again. So this is going to be b divided by b. I here. L is the distance. And the cross product of these two is right now b positive x. Right? Because we have here a minus. Great. Good. What is the up one? Fu. Funny. Right? Okay. What is the Fu force? The same equation. I, and look for the catch. What is dl? Is dx at the x direction. But what is b? b is b0 divided by x. Now we have multiply, this is up. we have multiplies x values. No way around that. We need to solve this integral, right? So what is let's do the multiplication. This x versus y is the z direction, right? So we're going to have I x direction, b not, but what is the integral of x? 1 over x? Ln, good. Okay, so we have here ln, and we have the boundary condition, right? Which is b from a to b, right? So we have here b over a in the x direction. Good. Last but not least is to find, I'm going that way, is to find the lower beam. The lower beam actually.
Isn't that the z direction?
What?
It's not the x direction, it's the z direction.
It's, again?
Z.
Z, agree. It's here, note, it's z direction because it's x multiplied by y. Cameraman, follow me. The last one, fd, equal to I integral from a to b, the lowest value, the highest value, good. dl is dx minus x, right? Because we're going at that direction, the negative side of x. Again, we have multiply value of x in the direction of y. So this is going to be the same thing in the minus z, right? Minus z, so I, b, and ln b divided by a, right? Sorry. So what is the total force that the door will experience?
Yeah.
It's the sum of the forces, right? So what are the sum of the forces? So we have the total force it's gonna feel is equal to what? To what's the left side experience, the right, up, down, right? But I want to see something really cool. They are the same with the minus sign, right? We get it, the same thing, okay? Why? Because they experience the same magnetic field and the current just flip direction, right? So up and down, sorry, that way, okay? So they cancel out, but what we have in L and R are different because one experienced a bigger magnetic field, right? The one of A and the other one of B. So here we're gonna have these two equal to I B node L 1 over B minus 1 over A in the x direction. So what is the direction the door gonna